Okay, let's continue. Um, so let's say in the first case that we have a Ka for this acid of 2.00 times 10 to the minus 3. And so that means that, remember what we had up here, that Ka value is equal to x squared over 0.5 minus x. And because we want to avoid using the quadratic formula, that's the whole basis for this shortcut. We say that x is negligible compared to the initial concentration 0.5, and so 0.5 minus x is about equal to 0.5. So now we can go ahead and solve this equation, solve for x, and we find that x squared is going to be 0.001, and so x is found to be the square root of that, 0.0316. So can I get away with this? I have to check. So I check to see if my change, x, is 5% or less of the initial 0.5. And so I'll take 0.0316 and compare it to the 0.5 and multiply by 100, so I get now a percent. It's actually a percent ionization. So we've seen problems like this before. So let's see if the percent ionization is 5% or less. Well, do it on the calculator. We get a little over 6%. And so x is not insignificant, really, compared to the 0.5. And so therefore, the 5% rule in this case is not valid. And I kind of set it up this way because we know from using a lot of acid ionization constants that 2 times 10 to the minus 3, that seems a little large as far as weak acids go. And so if we do it the short way and see that this is greater than 5%, then we have to go back to the quadratic formula. And so I would have to disqualify this part and focus on this side and solve it that way. So that would give me, therefore, 0.001 minus 0.002 minus x squared is equal to 0. So I would have to use my quadratic formula. A would be a minus 1, B a minus, and this is just an example, that's why my significant figures here are little x. And if you plug that into your quadratic formula, you will get two possible roots. You'll get two roots. One that's not possible, this one, because it's negative, and the other one, which is the correct answer, 0.0306. So that's the correct answer, 0.0306, not 0.0316. So they're not that different, and that's why usually the 5% rule works for us. So this is an example where the 5% rule does not work, and we have to use the quadratic formula. So up here where we said, let's say the Ka is 2 times 10 to the minus 3. Let's see if it works. If the acid dissociation constant is of the order of 1.23 times 10 to the minus 5. I'm going to let you work on that and see if it works, okay? Because that would mean that would equal, in the same example, x squared over 0.500 minus x, right? And we said, well, let's make that about equal to x squared over 0.5. Like, let's say that x is insignificant compared to the 0.5. So that means that x squared is equal to 0.5 times this guy, and we'll take the square root, and we find, see how you don't have to use the quadratic formula now. So we find that x is equal to 0.00247. So whenever we find x using this 5% rule, this assumption, we need to check our assumption. We need to check this validity of the 5% rule. And so let's take this change and put it over the initial value. That's a fraction. Let's make it a percent. So now it's a percent ionization. And it's very small. It's only about 0.5%. So in this case, because that k is much a smaller value, the 5% rule works because our assumption is valid because the percent ionization is less than 5%, way less. It's only 0.49. Okay. So hopefully that clears things up for you. And oops, on a related issue, we have the Henderson-Hasselbalch equation. So maybe I'll just keep this going. And this Henderson-Hasselbalch equation, again, for a buffer using a weak acid, let's say. I'll just write this out. Ka H3O plus A minus. Okay. And so we know, let's just go through the motions here. We know that Ka is equal to the H3O plus times the A minus divided by, and because it's all a product, I'm just going to set it up like this. Now, okay, usually I draw the line all the way over here, but it doesn't matter that I haven't. And what I want you to do is to think about taking the negative log of this whole equation, so both sides. Okay? Let's see what happens. Let's take the negative log of both sides. So what is the negative log of Ka? That's the pKa. What's the negative log of the H plus concentration at equilibrium? That's my pH. And if you take the log of something times something, that's the same as taking the log of this plus the log of this. Okay. And I'm taking the negative log of both sides. So this will be plus the minus log, or simply minus the log, of A minus over HA. And these are conjugate acid-base pairs. So if I wanted to call one the base and the other the acid, I can do that. And now this formula is going to look very familiar. Hopefully. And it also points out to you that there's no need to memorize it. If you can do that, you can do this. Okay? And this is our Henderson-Hasselbalch equation. The pH of a buffer made from a conjugate acid-base pair is equal to the pKa of the conjugate acid. Sorry, let's say that again. I need to rearrange these first. So the pH of the buffer is equal to the pH of the buffer is equal to the pKa of the conjugate acid. Now I'm going to bring this part over here. So now that's going to become a positive term. Now it looks a little more like your Henderson-Hasselbalch equation, doesn't it? Okay, we're recording live. All right, so the pH of, to restart, the pH of a buffer made using this conjugate acid-base pair is equal to the pKa value of the acid plus the log of the concentration of base over the concentration of the acid. And why does this equation have anything to do with the 5% rule? Well, you tell me. What are the concentrations that go in here? What units? Well, they're obviously supposed to be the equilibrium ones. But the equilibrium ones for the base and acid, let's just refresh your memory here and see what these would be. H3O plus and A minus. Okay, so let's say that we were making a buffer using 0.5 molar HA and 0.5, 0.52, I don't want the numbers to be exactly the same, molar A minus. Okay, we don't care about this. And initially there's nothing there. So we would have a minus x plus x plus x, and at equilibrium 0.5 minus x, x, and this 0.52 plus x. Okay? All right, so you see exactly where this is going now. You see how I have to deal with this? So because my Ka for this weak acid is small, I assume that x is less than 5%, or that the acid is less than 5% ionized, and therefore this amount of change is insignificant compared to its initial value. So what goes into my Ka equation? I simply put x times, instead of doing this, I say that this is about equal to x times 0.52 over 0.5, and then I solve it, and that's exactly what we've done up here. See how these are basically my initial concentrations because my change was insignificant? So in the Henderson-Hasselbalch equation, we are actually using, it's supposed to be equilibrium, yes, but we're actually inputting the initial numbers because x is not changing it very much. So for this buffer equation, the Henderson-Hasselbalch equation, it implies the 5% rule being valid. So there you have it. And is it always valid for our purposes? Yeah, because these Ka values are always 10 to the minus 5 and smaller. If they are greater, then you say, you know what, I'm not going to use this equation. I'm just going to write out the normal Ka equation and solve it that way. Okay, so remember, if you have any more questions on that, just pop me an email.